units, so I'm going to be very quick about it, but you have a graph, a directed graph, and typically it's without cycles, and you have input units, and you have outputs, and what you do is, given the each of the nodes in the graph has an activation value, AI, and you set the activation values on the inputs, and each unit computes, each unit makes a small computation from the input it gets, iteratively, so you fix the value of the activation on the inputs. Each unit performs some computation, and each unit combines the input it gets according to a given formula, and the formula depends on the parameter theta at the given unit. So, for example, you could take a linear combination with weights theta j of the incoming activities at a given unit, and then apply, in typical case, non-linearity to get value either 0 or 1 for the activity aj, and then you do it again all along the network. You have typically quite large graphs of this, each performing a small computation. It's a simple model of a very simple model of a brain, hopefully, and then you get an output. And the goal is you have a set of input output pairs, and the goal is to adjust the parameter theta used by the computation at each unit so that you get the output you want on a given input. And so this is used, for instance, for handwritten digit recognition. If you write a postal address on your postal mail, it reads the numbers on the envelope, and it takes this as an input, and as the output you have the abstract number instead of the image of the handwritten symbol. And this works actually in practice. So you want to train your network on a set of given inputs, outputs, with known outputs, and then you use it on inputs with unknown outputs. So actually what you get is that for each input, the network defines a probability distribution for the outputs. I mean, you have this handwritten digit, and the network says, I think this is a 9 with probability 80%. And so the network, all the parameters theta j of each unit define a probability distribution theta on the output given the parameters. And so you can train this using p theta on the output space, and you can train this using the natural gradient on p theta. You can view each theta as defining a p theta and make a gradient descent. You can compute the gradient actually in this case by a technique known as backpropagation, and then apply the Fisher matrix to update theta. So this was put forward by Marie, and the problem is maintaining the Fisher matrix of theta is quadratic in network size. So this is unacceptable. Last year Google did an experiment, I don't remember, but they had, I don't know, hundreds, thousands or maybe millions of units in the network, and so there is absolutely no question of using the Fisher matrix in that case. So people in practice do not use the natural gradient. They use the derivative, the obvious derivative, the obvious gradient ascent with respect to the numerical representation of theta. And one consequence is that if you make a change of basis, you change the learning trajectory. You change the trajectory of your training model. So, for instance, if you test the handwritten digit recognition, if you train it on white digits on a black background or black digits on a white background, this is a transformation x of 1 minus x on the inputs. This is a non-orthogonal transformation on the parameter space, and this results in different learning trajectories. It works better with black digits on a white background than the other way around. From information theory viewpoint, this is stupid because the information content is the same, whatever the color is. And so if you use the natural gradient, it works much better actually. But the problem is you cannot use it with a large network. So I'm going to stop here. I'm just going to say that last year I've done a lot of work on defining reductions of the natural gradient of the Fisher metric and of the natural gradient that are scalable to large networks and that keep the key invariant properties of the natural gradient, that is, it's completely intrinsic and canonical and does not depend on a numerical representation of the parameters, but only on, you define a metric based on what the network does, rather than how it is represented as numbers. And so I've tested this empirically for modeling on recurrent networks, and recurrent networks, they model sequential data sequences for sequential weather prediction or text prediction, for instance. And recurrent networks has a reputation for being completely impossible to train, but this works. So the natural gradient works for these instances. I'm going to stop here. Thank you.